It's great to be involved into this presentation, and thank you for inviting. So let me start by giving you a quick introduction of what we are doing, and then I will delve a little bit into the AI, and our main interest is regulation. So how do we regulate these vehicles? So I will go a little bit more in detail into that aspect. Before I go in the presentation, let me acknowledge, I would like to acknowledge the traditional owners of the land from where I'm presenting this today. And I would also like to acknowledge the Aboriginal and Torres Strait Elders, both past, present, and acknowledge any Aboriginal and Torres Strait Islander people who are listening to this presentation or may listen in the future through the recordings that's being carried out. Just a little bit of an introduction of the department where I work in. So as the slide said, I work for the Department of Transport and Main Roads in the state of Queensland. Within Australia, we are known as a sunshine state. We have plenty of sunshine, but not today though. Now I got a couple of minute YouTube video I'm gonna play as an introduction, and which will basically let you know about what our department does. It's a couple of minute video, and I hope the sound also comes through.
Queensland, home to more than 5 million of you. We're connecting you from A to B by more than 33,000 kilometres of state-controlled road, 6,000 kilometres of rail track, and 130 million public transport trips each year. Our job, no, our passion, is to deliver a network that is accessible to everyone at every age or stage. We're investing more than $5 billion to improve our transport infrastructure, making your roads more flood resilient and bringing new ways to pay, so you can use our network your way. We're making your health and safety our top priority. We're always listening to you, creating more online services than ever, serving customers online over 11 million times each year. We've kept the state moving, transporting more than 1 billion tonnes of freight, adding 27 kilometres of new cycling infrastructure, and building 9 new boat ramps, pontoons and jetties. We're investing more than $1 billion to maintain and improve our network operations. We're recycling over 1 million tyres and using them to build our roads. We're switching more than 35,000 streetlights to smart LED technology. We're creating a transport system that's environmentally friendly and socially sustainable, investing in skills, creating jobs, and embracing new technology. Queensland, we're here for you, to connect you to family and friends, schools, work and hospitals, to create a single, integrated transport network accessible to everyone.
Right, now my role in such a large and vast department is leading the cooperative and highly automated driving pilot. We're back in, I think it's about 2016 or so, when a lot of the car manufacturers were coming up with some fantastic statements which they struggled to fulfill. We can have now with the benefit of hindsight. And those days we were a little bit concerned about what we as a department are doing to ensure that this technology and the vehicles are rolled out on our network in a safe manner. And so the entire work, which we started initially from 2016, it ended up with a team called Cooperative and Automated Vehicle Initiative Team. And within that team, we have several projects which focus on connected technology as well as on automated technology. And my role is I lead the automated side of those technology. Now, fundamentally, why as a government we are doing this role, and that's a question we've been asked often, and that all goes back to our Queensland Department's road safety strategy, which aligns with Australia's national road safety strategy. We have a target. By 2030, we would like to reduce our road fatalities by 50% and serious injuries by 30%. Now, that is an ambitious target. Our vision is reducing it to zero by 2050. Now, these are very ambitious targets, and to achieve that, we need to do everything into all the themes that you can see in front of you. That is, improving our infrastructure, vehicles, as well as educating our road users. So when you look at the theme of safe vehicles, that's where our focus is, my project's focus is, which is cooperative and highly automated driving pilot. Now, when we think about automated vehicles itself, let's look back into the history and how automobiles or vehicles evolved. So the first production car was patented by Carl Benz in 1885. Which was a single-cylinder, four-stroke gasoline engine. And I mean, at that time, there were several cars were introduced, but this was the first patented which went into production. And Carl Benz, who took out the patent on it, and that company ended up as today's what we know as a Mercedes-Benz. Over the years, the automobiles have evolved significantly, and over 135 odd years, this is what today's vehicles look like. They're totally different, but when you look at it, when you scratch the surface, the fundamentals are very similar. There had been significant improvements, but there had been one unreliable component which existed in 1885, still exists in today's cars, and that is a human driver. So much so that in 1885, when Carl Benz was actually demonstrating his motor wagon, he actually crashed into a wall during demonstration, potentially the first recorded road crash in the history of automobiles, I would say. While the automobile technology has improved significantly, on the other end, in the meantime, the computer technology has evolved many folds. If you look at the computer of the day in 1885, that's Thomas arithmeter, was basically a mechanical calculator, and compare that to today's computers. So I have on the slide NVIDIA's Orin chip, which packs some 17 billion transistors and 200 trillion operations per second. I've seen NVIDIA's some late presentations, and they have now got a new one. I think they call it Thor, which is 5 times faster and packs in, I think, 50 plus billion transistors in 1 square inch die of the silicon chip. Now, this is because of this massive transformation and development in computer hardware and software. This is the first time ever that we could think about either replacing that unreliable component in automotive, which is a human driver, or supporting a human driver. But at the same time, we know that when you introduce a new technology in the mix of our current road infrastructure, as well as our current vehicles and road users, it comes up with new risks. And we need to understand those new risks so that when this technology arrives on our roads, that we have appropriate mitigations in place. And because of that, when we started thinking about it in 2016 or so, we came up with this project, and we call that as a cooperative and highly automated driving pilot. As it actually started in we done a lot of negotiations and other things, but it actually started. Agreements were signed with our university partner, Queensland University of Technology, and our federal government research institute through a federal government funding. It's called IMO Australia. So the scope of our project, and as I said, our focus is safety. So our scope of our project is trying to understand impacts and benefits, so basically safety impacts and benefit of cooperative and highly automated driving. And in that particularly, we were focused on what are those benefits or impacts on road infrastructure, and that is physical infrastructure. Then we also want to have a look at it. What about digital infrastructure? And that is a work package too. So we have several work packages in the pilot. Then the impacts with interactions with other road users. So we acknowledge that in Australia, although we acknowledge that in Australia, we would have a unique Australian conditions, and for that there'll be some unique solutions that needs to be developed. And we wanted to understand what are those unique Australian conditions. So, for example, we know in Australia, we currently do not have any automotive manufacturer. We basically import all our cars. So we recognize that the technology is going to be developed either in the United States, Europe, Japan, or China, and we will be the consumers. So we just wanted to make sure when the technology is being developed overseas, those technology developers ensure and make sure that certain unique Australian conditions are appropriately taken into account. And then another work package looks into human factors aspects, basically the handover, driving task takeover and handover related aspects. While we are delivering all these work packages, we also took the opportunity to demonstrate the technology to the public. And the intention is that sometimes in 2025, 2026, we might need to do some mass communication so that our public is aware that there are various types of automation, and all of those vehicles with various mix is on our roads. And along the way, of course, we want to grow our own knowledge as we go. To deliver these projects, we have developed two research platforms. First research platform is Zoe One. Now, this is Renault Zoe, so it's electric car, which you can buy from the local dealership. A standard electric car. There is no high tech on it, and the Zoe One, we instrumented it with state-of-the-art sensors. So you got a 360-degree cameras, lidars, highly sensitive GPS, perception systems, and computers, and all that to go with it. And what is to underline, this vehicle was never automated. This was like human-driven vehicle, but was designed to collect data just to ensure and test out our physical infrastructure, and then what we need to do. And then we developed a second vehicle, which is highly automated. Again, this is also based on the Renault Zoe platform, electric vehicle. And then this one was developed by our partner in France, a research institute called Vidicom. And they integrated all the sensors. I was fortunate to go to France and build the vehicle, calibrate it, test it, validate it, and bring it back from France to Queensland in Brisbane. The vehicle is a research prototype. So of course, there is no level 4 vehicle you can go and buy, and we can't wait because that's going to be too late. So we made sure that we have an access to this research prototype, which can be, so we have a full open access to all its algorithms, except some low-level safety critical algorithms. And we program the vehicle ourselves, and we can set it up based upon our research needs. level 4 based on whatever is our research scope. So we have this particular platform available, and the one of the most important aspect of this platform is that it's an open architecture. So we have access to every bit of data the vehicle generates. We can program ourselves, we can write our own algorithms, and test and validate ourselves. So when sorry, I'll go back to that slide again. So when you look at all of these work packages, what we're trying to work out is, as I mentioned, that our focus are 4 specific work packages. And in looking at the physical infrastructure side using Zoe 1, we actually drove the vehicle for about 1,200 kilometers on the Southeast Queensland road network in a daylight, in a day and night, various weather conditions in a rural environment, urban environment, highway environment, and tested 4 separate competencies. First one being road lines, road signs, traffic lights, and accurate localization positioning. We took whatever was available as an initial stage. We took algorithms which were open source, and then we trained them ourselves to work out what are the limitations of those algorithms for those particular competencies. So for example, we used, this was done in 2019, we used LaneNet. It's an open source algorithm. We trained it for our road conditions, for the line detection, and with a little bit of training, we were able to get very good performance about online detection. And why we needed to do this, we actually wanted to open the box of AI and understand how AI functions itself. So there was a lot of projects in Australia in 2019 where people were buying, off-the-shelf vehicles, and Audi, Mercedes, and Tesla, and so on and so forth, and then put a camera and then observe what the vehicle was detecting and then concluding. And we thought that may not be the right way to work out, because technology will change, and that doesn't, we cannot keep on changing our road infrastructure for the evolving technology. So we said, instead of that, let's question the technology itself. So let's open up the black box of AI and question its own capability, and that way we can draw conclusions whether we need to change our lane standards, the way we paint them, width, retroreflectivity, contrast, so on and so forth. And we done the similar things for sign detection, traffic light detection, as well as accurate positioning. Our reports are now public. It is available for public consumption. Our conclusion was that currently there are 2 philosophies emerging. On one side, the philosophy is that you do not need high definition maps or LiDAR for highly automated driving. And that's one side of the argument. On the other side, the argument is you will require high definition map, or let's call it a prior map, some sort of a map, and LiDARs to achieve high level of assurance for the highly automated vehicles. So the first philosophy is prescribed by Tesla, and literally every other experts that we talk to do not believe that you could achieve high level of automation with high level of assurance without LiDAR and without some sort of a prior map. And the way the things are moving on, and if you might have paid attention to latest, I think it was 2022 Tesla AI Day, and they showed some of the technology behind their autopilot, FSD, whatever you want to call it. They actually already now have some sort of prior maps as part of their automated driving. So that philosophy initially, what Tesla was saying that you don't need it, may not be valid anymore. So what we're seeing is that the conclusions we arrived upon in 2019 is that if you're going to have no HD maps and no LiDARs, you will need to do significant investment for your physical infrastructure. But if you're going to have LiDARs and high definition maps, then you might not need to do a lot of investment. Basically, the technology will be evolving to a point to deal with and understand the current physical infrastructure which we are developing for human drivers. Then we are working on various work packages, which is work package 1 is, as I said, driving task handover. We have recruited several public participants representing various age groups and so on and so forth. They sit in Zoe 2. We actually encourage them to come along with a book, and Zoe to drives them around in a controlled environment. So we have a closed track, a test track, and Zoe, our vehicle, drives them around for about 33 minutes while they are, either reading a book or watching a video. And along the way, we also design an experiment where they need to answer some questions about the video they're watching. So, but what we're trying to do is we involve them in a cognitive way, and along the way, the vehicle triggers takeover request. And we have all sorts of sensors around, including the driver's gaze. And we do also analysis to work out whether the driver following the takeover request, how long, time-wise, how long does it take for them to exercise appropriate, so safe control, and come into the situational awareness. So we have done some, so far I think about 150 participants have participated, and we have some initial results as well. So all of that data is currently being analyzed, and potentially in a couple of months we would be in a position to make the report public. On work package 2, we are working on CITS, so connected technology integrating with the automated vehicle technology. We have picked up a couple of use cases, and we have collected a lot of data when we are doing at the moment Monte Carlo simulation and working out quantifiable benefit of having CITS and not having CITS. What is the safety benefit of connected technology integrated into CITS? So a lot of the data is already being collected, and modeling is currently going on. And again, in a couple of months, that report's going to be made public. And work package 3, as I briefly touched upon, is more about unique Australian conditions and what are the learnings out of it. And when we did the literature review, we thought that there are about 13 scenarios that are unique to Australia. Then we hired we engaged some international experts. So one person from the United States, one from France, and one from Germany, and asked them to review and say, look, do you agree? Because we think that about 13 cases are very unique to Australia. And their response was that out of 13, there are actually only 3 which are unique to Australia. And those 3 are our unique wildlife, especially our kangaroo, our long trucks. So we have road trains that are quite long, and we have some unique roads which are quite in the country, which are narrow, 4-meter wide sealed road, but we have unsealed shoulder, so where we have traffic in both direction into that narrow road. So these are 3 unique situations, and we have collected a few thousand kilometers worth of data, and now we are creating algorithms to deal with those situations and the learnings would be made public sometimes in August, September this year. So these are the kind of detailed work that we are doing with our cooperative highly automated driving pilot. Now, I understand that this group is more interested in AI and how that gets played out in automated vehicles. So I got a few slides on it. So the way the automated vehicles function, and literally this is from Waymo to everyone will tell you the same thing. They have a four basically blocks within which they work. So localization, knowing where the vehicle is into the world, perception, knowing what's happening around about that environment, and then decision making, and then control. So decision making is basically based upon various road rules, trajectory, estimated trajectory, estimating and creating a path forward. And control is basically providing information for the hardware, such as how much angle, steering angle, brake, acceleration, including the side lights and hazard lights, and so on and so forth. So localization, the way the things are currently being developed and carried out, you have lots of different ways of doing it. So you got a GPS supported by RTK, inertial IMU, and there are lots of different ways and different technology that you could use. You had a simultaneous localization and mapping, SLAM systems. Literally everyone uses them, and for that you will need some sort of a prior map of the environment to have fairly high level of accuracies. When it comes to perception, you got all sorts of sensors. I just listed a few sensors, but at the end of the day, what we need to do, all the sensors are used for object detection, recognition, and tracking, and then situation understanding via scene segmentation. I seen some companies use, some other sensors as well, microphones. They have some of them have an infrared camera as well. So there are different ways of doing those things. When it comes to decision making, things like road rules, predicting the trajectories based upon potential interactions that you have in the environment, various actors in the environment, and then control, as I mentioned, in a steer, brake, accelerator, and side lights, and so on and so forth. Now, when you look into each of those blocks, there is a significant amount of AI being used for localization and perception, and there's massive amounts of. But, and again, I would stress this is currently there isn't as much AI being used for decision making and control, and there are reasons for it. And the reasons are the way the regulatory framework currently works or is planned to be introduced. So in Australia, we are currently drafting our laws for automated vehicle introduction. And the model which we are using for automated vehicles is a co-regulatory model. And the main reason for that is allows innovation. Now, we have been regulating our rail industry through co-regulatory model, our maritime industry, our aviation industry. So we have a lot of experience in how do we regulate in a co-regulatory model. And into that co-regulatory model, the criteria we have is so far as is reasonably practicable, and that's our safety criteria. We are not prescriptive about how do you achieve that, and that way we allow the manufacturers, tech developers room to innovate. But at the same time, our draft codes clearly mention that the tech developers will need to provide a statement of compliance. So although it may not sound prescriptive, but there are technical standards that are involved, and the tech companies will need to adhere to it and will need to provide a statement of compliance. Now, one of the key difference between a prescriptive regulator and a and a regulator who works and discharges its duties under co-regulatory model is the word approval versus acceptance. So when you have a prescriptive regulator, the certain actions are or deliverables are approved, and that's the word being used. While in co-regulatory model, the word approved is not used. Instead, we use the word accepted. In other words, these are your claims, this is your statement of compliance, and we ask a lot of questions, and then we accept, and then we provide permit, or we don't accept and we don't provide permit. So there's a major distinction between the model of co-regulation versus model of prescription. So as I quickly touched upon, so our codes require that AVs will need to provide a statement of compliance, and in that we clearly mention that it needs to be complied with ISO 26262. That is a safety integrity level. Although we haven't mentioned that it needs to be level D, but if you go to the level and automation level 3 or level 4 kind of an automation, it is expected that the safety integrity levels would be at level D, which is a probability of dangerous failure between 10 raised to the power of -8 and -7 per hour. Now, this is nothing new because industry has been working with similar standards for years. I have been working in the rail, and we have safety integrity levels very similar to this. Now, the probability of dangerous failure of 10 raised to -8 to -7 is actually being demanded by OEMs for the tech suppliers. So if you look at if you ask a Mobileye who develops this technology and provides it to various OEMs, they will tell you that OEMs are actually demanding 10 to the power of -7 mean time between failures. So this is coming from ISO 26262. And now ISO 26262 actually deals with systems. In other words, you have steering systems, you have all sorts of different systems. And it is more about systems. In other words, one system fails, there needs to be redundancies. And this is the main reason. If you look at the only commercially available level 3 vehicle at the moment, and I need to be very careful. So it's commercially available level 3 vehicle which one can own, because you got a Honda Legend in Japan, which you cannot own. You are basically leasing it from Honda. But one which you can own, one which you can own is a Mercedes S-Class in Germany. And now I understand that that in Nevada, in the state of Nevada in United States, it's available, or it's gonna be legal very soon. And so if you look at the specification of a level 3 S-Class, they pay a lot of they keep on they highlight the fact that they have a redundant steering, braking, and braking system, as well as redundant onboard electrical systems, to ensure that it remains maneuverable even if one of the systems fails, and then it allows you for a safe handover to the driver. Now, that is a key difference between your level 2 or below vehicles. There is a lot of work and assurance activities one need to do to make sure that redundancy in systems is available. And then you have another ISO standard, and that is also part of our code, is a 21448. It's a SOTIF standard, safety of the intended functionality standard. And that particular standard is it applies at algorithm level. In other words, your operational design domain, let's say it's a vehicle being sold in Queensland, where we have basically sunny weather, which is most common, uh, and we never have snow as such. But in case there is a hailstorm and we have a road, full of hail, which is white looking ice on the road, the system and algorithm should fail safe, and that is a requirement of SOTIF. All of this is required that OEMs will provide us statement of compliance, and that compliance statement will come from an independent, respectable engineering firms. Now, another requirement from our regulation is IEEE. Sorry, it's not a requirement, but it is something what industry has put together, and we will, as a regulator, will need to have a look at this one, and that is P2846. So P2846 is a standard for assumptions in safety-related models for automated driving. I have a slide on that, so I'll to save a bit of time, I will jump straight onto the next slide. But in all of that, our regulation also requires that you must have a safety management system. That is to ensure the fundamentals of so far as is reasonably practicable. In other words, if you find some issue with your system, your safety management system should proactively try to resolve it and reduce the impact of it, and then it should not be reproducible again. All that is part of our current draft codes. So I'll just quickly go into the decision making, and I touched upon 2846, and I said it's not part of our regulation, but it will be expected from from the tech providers that this is being implemented. And the reason being is that how safe is safe enough? This is the P2846 is actually an initiative by the tech providers, the industry. So the working group which put together this standard involved from chip manufacturers to software designers to tier 1 suppliers to OEMs, literally everyone in the world, except one notable company being Tesla. Everyone got together and basically said, well, how safe is safe enough? So along the way, somewhere, we will have to make some decisions. And so far as is reasonably practicable, that criteria, what does that mean? I mean, how safe is safe enough? So with this standard, so let's say currently our rule saying that when you're following another vehicle, you must maintain safe distance, and generally that's about 2-second distance. Now, when we say 2-second distance, and when you look at the rule-based decision making that is currently in place, there is an equation, and in that equation, the automated vehicle would needs to assume the vehicle ahead and its braking characteristics. And the problem we have here is that you have on the road vehicles, all sorts of vehicles. So if you pick up Porsche 911 has one of the best braking characteristics. Its deceleration rate is 12.57 meter per second square. And while you might have a loaded truck, which would have much less braking performance. So what is that number that automated vehicle needs to assume? If it assumes Porsche Carrera, all of them, then what you're going to end up is you're going to have a huge headway, and in a highway condition, other human-driven cars will start, cutting in front of you. It doesn't really help, and at the same time, you also reduce your highways capacity. So the way this standard particularly works is when you look at the NASA has found that although you have all sorts of different vehicles with different braking characteristics, humans actually apply their brakes at about 6.56 meter per second square. That's a kind of a standard that humans apply their brakes. So under P2846, the industry is saying that we will be assuming something like 6.56 as a deceleration rate. And as a regulator, tell us if you want something other than that. Now, why is this important? Is that there is no foolproof guarantee of safety. And something like this, if it ends up in the courts, the manufacturers can use these assumptions and under the so far as is reasonably practicable criteria, they can defend themselves. So my point here is that when it comes to decision making, there are at the moment very little AI being used. Lots of those decisions are rule based and that are equation based. So much so that some of the rules, I can speak about Mobileye, their low-level decision-making, and they call it RSS, entire code is made public. So you can go and investigate every bit of codes if you like. You can go to the publicly available carla.org, which is a simulation, publicly available simulation database, and you can import Mobileye's RSS, and you can test it out yourself as much as you want. So my point is that there may be a general perception that these vehicles are, the decisions are being made based on AI. That may not be fully correct. These are pretty much rule-based decision making. When you go to control, again, similar things. In the industry for 40 odd years, controls are being done through proportional, integral, and derivative PID controllers. And similar things is happening in automation as well. We use PI controllers for our steering control right now as we go. If someone wants to use end-to-end deep learning without forensic capability, currently we do not think that any engineering firm would give you any compliance certificate, because what are you measuring against? We have no capability to forensically test the outputs of that system. So I put one quick slide which shows the current level of automation. So we got 6 levels, so 0 to 5, but there's a ISO standard 2289989, which actually adds in 6th level of automation, which calls autonomy. And in that one, the system is capable of modifying its intended domain of use without external intervention. And we are nowhere near that. Now, just to give you an example of what does that mean is, let's say I'm driving my highly level 4 automated vehicle on a highway. I'm as a human, I'm driving, and there's a truck ahead of me, and I can see there's some loose load which may come loose and fall in front of me. I see that, I understand the situation, and I take some action, although there's nothing fallen yet, but I take some action. Now, think about an automated vehicle the way they are designed currently. Now, the way they are designed, if they are not trained for such situations, they're not going to do what I did as a human. And interestingly, I as a human, let's say I've been driving for 30 years, and this kind of a situation I have never come across. Still somehow with my growing up and various learning, somehow I was able to apply that and work out that I need to move away from here. But the AI, the way it is currently, will never do that, because if they are not trained, because they are trained in a driving environment, and this kind of training was never part of its algorithm, it's never going to do it. But if you end up with level 6 autonomy, then it's beyond AI. Then you are into AGI. It's not just training through your driving, it's general AI. It's beyond just driving. So that's a little quick example, and we are a long way from it. None of our regulations will currently would be able to deal with it. So that's where we are. I think that's all I have to say, and I'm more than happy to take any questions.
Thank you very much for that presentation. It was extremely informative and my congratulations to you. We have 113 people on the webinar. So in case you wondered whether or not staying awake until 8 o'clock at night was going to have any value from our standpoint, the answer is yes. The forum is open. I guess you can either put a question in the chat box or you can raise your hand. I think if you raise your hand, why, I'm guessing that you will sort of surface, maybe is the right word, in terms of visibility, so that we can let you have the floor to ask a question.
So I have a question about the safety analysis you talked about toward the end. I think the situations are so diverse, and especially when there are, human-driven legacy vehicles in the mix, it seems like you would need not just adaptive reasoning, but you need some sort of game theoretic kinds of reasoning, and in the sense that I think, building on your example, that if the vehicle were to leave a large amount of space in front, it would quickly be taken over by people, and so it'd be left with not so much space anymore, or it would just lead to more vehicles cutting in front, which should not enhance its safety. So somehow it has to adaptively learn the sort of the social makeup of the other vehicles and on the road, and maybe create some sort of a convoy or do something with the vehicles that happen to be around at that particular time.
Yes, that's correct. I mean, this is where I said I'm focused on more the way things are currently. But if there are more tools and standards evolve further, which allows the engineers to certify the adaptability of your algorithms through some sort of forensic ability, then engineers will be comfortable to certify. But the way it is currently, I don't see it. The current structure isn't designed that way. And the question about, you mentioned, the P2846, there are lots of different ones. So what industry is saying that there is nothing called 100% safety. There's nothing called absolute safety. So there has to be some assumptions. And this is what we propose under P2846. If you as a regulator want us to use some other numbers, we are more than happy to. But if we would keep on sort of make it more stringent for ourselves and improve more and more safety, the vehicle would behave, in such a way that no one would accept it. So there is a bit of a balancing act into that.
Yeah, thank you. Yeah.
Sasha asked a question that's probably information related. She says she doesn't completely understand the difference between accepting and approving of permits and safety compliance. Is there a easy explanation for what's the difference between accepting and approving of permits?
Yes, in a nutshell, approving means the approving agency is taking responsibility, while accepting is that your claims, I am accepting it. Although I need to do due diligence as a regulator, but you are the one who are providing me statement of compliance. I will be asking you lots of questions. I have worked for more than a decade in the rail safety regulators office here in Brisbane, and that is the way we have regulated for long time. So that's the main difference. Approving part is where you approve, you have taken responsibility about it, while accepting is you accepting their claims.
Yeah, that's a really important distinction. I can relate to that from a railroad perspective as well. Adam Goeta, I think is how you pronounce his name. So when dealing with Australian novel scenarios, how do you design experiments for loosely secured cargo falling or kangaroos? He said, I don't know about the kangaroos, but no, they're there. But
kangaroos
are very good question.
Yes, kangaroos are a very interesting scenario. So there is no problem whatsoever in detecting a kangaroo. there is almost no problem in classifying it as a kangaroo. Problem comes up in predicting what kangaroo is going to do next. And that's a problem for humans today. I don't have answers. We have a limited data. We have a, because the vehicle what we have, our platform is very expensive. We only have one. We have our insurers have put some strict conditions, so we are unable to go out and collect a lot of data on the roads where there are a lot of kangaroos. So we are forbidden. So I don't have a lot of data. So to answer your question, the challenge still remains. So, and again, I would highlight that it's not a challenge of detecting and classifying. It's a challenge of predicting what it's going to do next, which we humans still struggle.
Sasha Azad has a question. Sasha?
Yeah, just a follow-up question on that. So you mentioned it's hard to go out to roads and actually collect a lot of data on these kind of situations. Have you considered using simulated data or simulated towns to kind of collect this data, or like feeding in simulated data into your models to see whether it's kind of recognizing these situations? Because I know, I think it is Google's autonomous vehicle group is kind of using I forget which, but like some game scenarios and cities to test their own algorithms.
Yes. So we have tool sets and a validation suite, the entire suite in our offices, where we can simulate and all these kind of scenarios. So to answer your question, in short, our current project, we had a budget to resolve only one scenario out of three. As I mentioned, there are three scenarios, and one scenario which we picked up, which is much more priority for us, is long trucks we have, what we call as road trains in Australian roads. So that's the algorithms we're developing and testing it out. So, and we do not have at the moment funds to go into resolving a kangaroo scenario. Unless I have a funds, I would not be able to go into that and do simulation. And again, I can only see the way we can do it is through simulation.
Yeah, I think I was just looking up the news article. So Google uses Grand Theft Auto, one of the to like get city simulations of like children running out onto the road and so on to test their algorithms with. But yeah.
Yep.
Thank you for that. Joseph, you want to ask your question?
Hey, yeah. So you mentioned that IEEE 2846, one of the notable automakers that's not participating in it is Tesla. I just wanted to know if you have any insight regarding that.
Interesting question. When we knew a couple of years ago, when we knew that the IEEE 2846 working group was there, we were very excited, me and my colleagues in Queensland University of Technology, and we tried to get a seat into that working group. Unfortunately, since we are not the members of IEEE, we were not given the seat, so I don't have that information. No, so sorry, but I don't know why.
Yeah, thank you, anyway. Thank you.
Adam, you had another question.
Yeah, and thank you very much for giving this talk. So I teach our Introduction to AI course here at NC State, and specifically one of the things that I'm going to be covering later on in the semester is ethics in AI. And one of the things that I use as sort of an example is specifically when we look at autonomous vehicles, we at least open with the question of who is at fault. So in the event of an accident, I know you talked about forensic capabilities in your decision making is it sounds like a requirement by everybody. Has that been a discussion on your end about just in that event where an accident does occur? Sort of where does that fault lie? Does it lie in the software makers? Does it lie in the manufacturers? Does it lie in the owner of the vehicle, etc.?
Yes, the way we are drafting our law, it basically requires there is we have some terminology. So what we call is ADSE. For an automated vehicle, so ADS, automated driving system, there can only be one ADSE, which is automated driving system entity. So they cannot say that it's someone else's responsibility or someone else's fault. Once it is found that it is an ADS's fault, which is automated driving system's fault, then you as an entity, you need to answer. So that's how our laws are being designed. And I stress they are not available. They are currently under drafts, and our people, legal people, are going through it, and we're drafting it. Hope it answers your question.
Ali, you have a question.
Yes, George, thanks. And thanks a lot for this very informative presentation. I want to ask a question about the two different philosophies of automation technology that you talked about. One, using LiDARs and more sensors and HD maps, and the other one relying on less expensive sensors, but improving the infrastructure. I wanted to see, how do you think using either of them is gonna influence the adoption of AV technology? Because if we think about expensive sensors from one side, like the price of the car is gonna be much more expensive. If, for example, you think about a car that we can buy for 20K, a LiDAR is gonna significantly increase the price. But the other side, investing too much, also it requires too much investment in the infrastructure. So how do you think these two are gonna influence the adoption in the future?
I think the question is more, I mean, the pricing structures and business models is something what industry will need to work out. We as a regulator in the government sector, what we are interested in is assurance, safety assurance. If it can be done safely and demonstrated so far as is reasonably practicable, that's our criteria, then it should not be done. So whether it is a sensor side of things, having more sensors and all that is going to be more costly, so and so forth, it's basically nothing to do with the regulator. Regulator will say, well, you can't demonstrate so far as is reasonably practicable, then you will not be given the permit. Now, the question, what you said was that how about government spend lots of money on the infrastructure? Now, the issue is actually, if you go back into there's interesting history. Way back, it was so 1885 was the first automobile, motor wagon. Exactly 100 years after, the first automated car was demonstrated. I think it was Carnegie Mellon University in 1985, and exactly same time across the ditch in Europe, the European manufacturers started a project. And there's an interesting history. Europeans actually wanted to make that highways intelligent, and I forget the name of a professor. He actually convinced them that you do not need to do that. All you need to do is make your cars intelligent. And they exactly same time they also demonstrated just through camera you could deliver automation, and you don't need to improve your you need to make your highway smart. So my answer to that is, where is the line? I mean, if we want to start making our highways intelligent, we may end up as a closed infrastructure. We may end up pretty close to like what we do in rail. So again, this is a debatable thing, but what I know, if you would, the latest CES 2023, Professor Amnon Shashua from Mobileye gave a presentation, and they are targeting by 2025, 2026, full ADS, level 4 highway ADS for $5,000. And that's for the OEM. So by the time it comes out on the dealership, it would be about $10,000 USD, which is equivalent to what Tesla is charging at the moment for the level 2 FSD. So I don't think that the sensor side of things is going to be too expensive. That argument might cut.
I think we got time for maybe one or two more questions. Jungfeng, you have a question?
Okay.
Yeah, just a very quick question, and thank you, Adria, for your presentation. So you mentioned that there are a lot of common driving situations, but also there are some situations that are unique to Australia and you need to collect data. I'm wondering, when you are training like AI algorithms, do you use those common situations are unique to other countries and not available in Australia? For example, we know most countries drive on the right side and Australia drive on the left side. So is there any impact of those data on training your algorithm? That's my question. Thanks.
So I mean, driving on the left and right side it doesn't really make that much difference. That's our experience. I mean, when we brought Zoe to was built in France, and when we brought here in France, they drive just like America. They drive on the right side of the road, and we do on the other side. When we brought it here and we did all the tests in the closed, safe environment, we found we had issues at the way the car was negotiating roundabouts and all that. We need to change our algorithms and so on and so forth. But no, we managed to do it quite quickly. It didn't really take that much time and efforts. But matured tech companies, they pay a lot of attention to all this. Companies like Mobileye, and I'm quite sure Waymo and others would be as well.